So I actually had a dream last night that I was trying to explain today's lecture to small children. It was weird. And I'm not sure how well it went there. We're talking today about infrared spectroscopy. Unlike mass spectrometry, infrared spectroscopy is something where you actually do shoot light at a sample. The sample absorbs light, and based on what wavelengths of light get absorbed, you can infer some things about the structure of the sample. This is actually an experiment you will do if you take the 353 organic lab, and it's a really fast and cheap and easy way to determine the presence of some functional groups in your sample. We're just going to scratch the surface here. There's a ton more about infrared spectroscopy. If you want to learn more about that, P-Chem, physical chemistry, is a good place to start. But for now, you've got the electromagnetic spectrum, you've got infrared light, which is a little bit lower energy than visible light. Visible light and UV light can excite electrons from HOMO to LUMO. We call those electronic transitions. Infrared light is not energetic enough to do that, but it can excite other transitions in the molecule. We won't have learned about these yet. The transitions that get excited by infrared light, or the things that change about infrared light, are bond stretching and bond bending. So you can think of atoms and bonds like springs. Now we've learned about bonding, we've learned about electrons in bonding orbitals holding nuclei together. But if you take a step back and just look at the two atoms held together by a bond, they start to behave a lot like a Newtonian spring. And if you learned about that in physics, the vibration of a spring depends on a force constant, how strong the spring is, how tight the spring is, how much it resists movement, and then it also depends on the masses at either end of the spring. There's more physics there that we could talk about that we won't, but these are different ways that bonds can vibrate. There's stretching, which is just this kind of action on a spring. And then there's bending, where a bond angle changes based on movement of the two atoms. And both types of motions have this sort of spring-like capability. If we go to the, where did it go? I used to have, isn't that cute? That's me and my wife in Disney World back in the days of COVID. Let's see, molecules. Yeah, I was going to show you the gallery of molecules. I mean, you guys didn't even go, oh, that's okay. We're not really feeling it this morning. That's fine. So you can see, if we slow down the time scale, but we turn up the temperature, you can see bonds vibrating and you can see bonds bending. So stretching back and forth along the axis between two atoms, and then bending of atoms in a bond angle changing slightly. So these are called vibrational modes, or vibrational energy states. And they are like all other energy states, they are quantized. And so if you have light of the right frequency, you can excite one vibrational mode to another, and the light that gets absorbed is infrared. Now we'll go back to here. You can describe the wavelength or frequency of light that gets absorbed in spectroscopy in multiple ways. Because light, the speed of light is equal to its wavelength times its frequency, if you know one, you automatically know the other. So in some forms of spectroscopy, they use frequency to describe the kind of light that excites a transition. In other forms of spectroscopy, they'll use wavelength. It really depends on whether you want to talk in frequency, which is hertz, or wavelength, which is meters. In the case of IR, for historical reasons, the wavelengths that excite vibrational transitions are in the range of 2 to 25 micrometers. People historically are not wanting to put times 10 to the minus 6 or times 10 to the 6 on an axis. And so sometimes they'll find creative ways to get the units to work out so that you don't have to use decimals or scientific notation. So the way that they've done this with infrared spectroscopy, as I told you last time, is you take 1 over the wavelength and then you express it in units of inverse centimeters. And all you need to know about this is this term is called wave number, and it's proportional to frequency, meaning I could frequency equals c divided by wavelength, and therefore the energy of a photon of light you could express in this form, or that could equal h times c times wave number. In other words, the higher the wave number, the more energetic the light is that excites that transition. So you can interpret wave number exactly as you would interpret frequency. Higher numbers mean more energy required. And if you want a physical interpretation of wave number, it's if you have a centimeter, how many wavelengths, how many cycles, how many wavelengths are contained per centimeter. Okay, so bond stretching. Now, what I'm going to show you here is not an equation that you're going to have to use for any purpose, but it's useful to know so you can have an intuitive sense for how to interpret an IR spectrum. The frequency of or wave number of light that excites a vibrational transition is related to some rate constant, and then under the square root sign you've got a force constant, and then the mass of the atoms in the bond. Okay? So let's deal with mass first, because that's easy. If the atoms weigh less, this number is smaller, right? And therefore, this number must be bigger, right? So we expect bonds that have less massive atoms on them to show up at higher wave number. In other words, a CH bond or an OH bond or an NH bond should stretch and vibrate at a higher wave number, higher frequency than a CC bond because the mass is lower, all right? So if we look at an infrared spectrum, as we will see it later, it's usually drawn in this fashion with low wave numbers on the right and higher wave numbers on the left. I realize that's backwards from what you expect, and I don't know why they do it that way. You expect bonds to hydrogen to show up at the highest values of wave number because of that Hooke's law where mass is in the denominator. Second, force constant, type of bond. Stronger bonds have tighter springs, more resistant springs. So stronger bonds should show up at higher frequency, higher wave number. So as an example, you would expect double bonds to show up at a higher frequency or higher wave number than single bonds, because a double bond, sigma plus pi, is stronger than just a single bond, just sigma. And this is true. If we look at an IR spectrum, we're going to see triple bonds show up at a higher wave number than double bonds, and we're going to see double bonds show up at a higher wave number than single bonds. In general, we're going to use IR to see what kinds of bonds with hydrogen we have and what kinds of double bonds that we have. We won't be really using IR to interpret what kinds of heavier atoms, single bonds we have, because there's going to be a lot of stuff here and it's going to be difficult to interpret. Okay? So what do we remember? Lower mass CH bonds, OH bonds, NH bonds, highest frequency, then triple bonds, than double bonds. Stronger bonds have higher force constants, higher frequency. Okay, let me give you some examples of types of vibration. These are from calculations I did on a molecule we were interested in, and it'll actually show you all the vibrational modes that are allowed for the molecule. This is just an animation of which bond is vibrating. I had to learn how to make GIFs. Is that my son says it's a gift, not a GIFT, so a GIF is a GIF. I don't know whether we have some pronunciation specialists out there. GIF is a peanut butter, and a GIF is anyway. So this is I had to learn how to do this. But anyway, this is the vibration of an OH bond here. And its frequency is, like I said, about 4,000 wave number. Here is an NH bond. Its frequency is around 3,800 wave number. And here is not stretching of a CH bond, but a CH bend. And these videos are fun because it starts to look like the molecules like dancing a little bit. This is not a CH bond stretch. This is bond angle bending, and that frequency is around 1,500. These are not things to memorize, but these are just examples. In contrast, what you've got here is a stretch of an sp3 hybridized carbon-hydrogen bond, and its wave number is around 3,000. Here's a double bond stretching. This is a carbonyl, and it's around 1,900 wave number. And in large molecules, some of these vibrations are coupled. For example, you see this carbonyl vibrating, and this one nearby is sort of getting its groove on a little bit too. The groove is a little bit contagious. Let's see, some more CH stretches. Here is stretching of a CC bond in a benzene ring at the same time as you're getting some CH bond bending, and that frequency is around 1,600. So all of this is not for you to memorize, it's just for you to visualize what's going on. And frankly, this is too much detail. As long as you look at an IR spectrum and you're like, okay, that is an OH bond going like this, most of what we're going to be dealing with and interpreting is bond stretching rather than bond bending. Okay, questions so far? Yeah? How do you know what part of the molecule is going to absorb the light? The answer is you don't until you do a calculation that can predict it. But then based on experience and based on those calculations, there are characteristic signals that are consistent with specific bond vibrations. And so once you know what those patterns are, you can then look at data for an unknown molecule and say, oh, I recognize that. That's probably this kind of bond. Yeah?
What are the numbers that you'd like us to know?
What are the numbers that I'd like you to know? Okay, well, here are some of them, and this is too many. Really, the most useful ones I'm going to highlight are OH, and then carbon-oxygen double bond. There are others that are useful, but the most useful are knowing whether there's an OH group and knowing whether there's a carbon-oxygen pi bond. The reason for this is that we have other tools for really getting in there and figuring out what all the sigma bonds are and what the connectivity is. So people don't use IR to get the right structure of the molecule. They do use IR to interpret functional group changes in a reaction. So just to review, you will see OH bonds in really high wave number. And this is a range of values. You're not meant to have a specific value here, just a range of values. The second thing we are going to see with IR is that it's not enough to have a range of values. You also need to know something about the peak shape, because you will see that IR peaks might be narrow and small. They might be narrow and intense, or they might be broad and intense. Those are different shapes of peaks you will see in an IR spectrum. By the way, you'll notice that I drew those peaks as valleys. What the heck am I doing? There is a reason for that that doesn't matter, but in IR, the peaks are all drawn negative like that towards the bottom of the page. The historical reason, I think I heard somebody whispering this, is that originally it's not absorbance but percent transmittance, what percent of light is getting through. So a peak means a low percentage of light getting through at that point. So anyway, yeah?
How might we use this knowledge to do like problem sets or questions on the exam?
I'm getting there. The key question, you're like, all right, I'm imagining you sitting there and saying, all right, Chuckles, cut to the point. What are we going to be able to do? Chuckles is my word for anybody I'm irritated with at the moment, like on the road. Oh, Chuckles over there doesn't want to let me in. My wife laughed at me because it makes no sense, but anyway, sorry. Yeah, let's get to the point. Before we get to the point, I just have to say, you will find this in your text. It will help you interpret things. There's going to be a table like this on your exam. It might not have the OH and the carbonyl. You probably will need to remember that. You'll thank me for that later when you're in the 353 lab. It's just easier if you know that one. So you need to know not only the range, but also the intensity of the peak. The OH peak tends to be intense or strong, but also broad, not narrow. There's a reason for that. We don't need to explain it. The carbonyl peak, the double bond stretch, tends to be strong. That is very intense, but it tends to be pretty narrow. And so generally you'll see descriptors of these kinds of peaks. Intensity, strength, strong, medium, weak is how far down on the axis does it go. And then narrow versus broad is whether the peak is sharp versus spaced out. Okay, so let me show you some examples. Behold, this molecule here, which I'm not going to bother to name because 2-methyl something or other, 1, 2, 3, 4, 5, 6, hexene, 2-methyl-1-hexene. All right. One question that you might be given is, which of these structures is consistent with the IR spectrum? Okay? So this one, this molecule C, has an OH group. If there were an OH group in this molecule, I would expect to see a strong, broad peak in this region. I don't. One of the things you'll get experience with is that in most IR spectra of organic compounds, there is a strong narrow peak in the range of 3,000 to 2,800, and that's usually just your boring CH bonds, which tells you nothing because all of these molecules have sp3 hybridized carbon-hydrogen bonds. So when you see a narrow, strong peak like this at around 3,000, you need to be thinking, I probably have some sp3 hybridized carbon-hydrogen bonds. And I expected that to be the case because this is organic chemistry and all organic molecules have carbon in them and CH bonds. All right? So that peak is there, it's interesting, but it doesn't help you distinguish between these three molecules. There's another peak that's present which you could analyze if you wanted to. I would tend to ignore it, but this peak is consistent if you go back and look at the table. This peak is consistent with an sp2 hybridized carbon-hydrogen bond stretch. It shows up at a higher wave number. Why? Because sp2 hybridized carbon-hydrogen bonds are stronger than sp3 carbon-hybridized bonds. They have a stiffer force constant. So that is consistent with a carbon hydrogen sp2 hybridized vinyl proton. Now, it turns out all of these have vinyl protons, so that doesn't help. However, B should have a carbon-oxygen stretch, and that would tend to appear in the range of 1,600 to 1,900, and it would be strong and narrow, and there's nothing there. So I infer from that that it can't be the carbonyl. Also, as I said, the lack of an OH signal showing up here gives me a sense that it also can't be the alcohol. So you're going to use IR to rule out possibilities. Yeah?
Does the number of functional groups in any way affect the shape of the graph?
Absolutely. Does the number of functional groups in any way affect the shape of the graph? Yes. In the ways I was saying, the absence of, well, no, I can draw it. If there had been a carbonyl group in this molecule, it would have shown up around here and been sharp like that. If there had been an OH group, it would likely have showed up there. Yeah? If there were two OH groups, can you tell the difference between 2 and 1? Probably not, because they probably occupy the same space and just sort of add together. There are cases where you might see multiple carbonyl peaks. I can't think of any that you'll encounter. So if you see a peak that's consistent with a carbonyl group, you may not know whether it's 1 or 2. Also, notice that this area here where the sigma bonds show up, we're not even bothering to interpret. It's generally too complicated. We call that the fingerprint region, and you can do calculations, but it's not useful if it's just you and your brain. But this area sort of above 1500 is where the functional groups that we're interested in show up. Okay, the best way to do this is just to look at examples and come back to thinking about what we would expect. So here, let's see, do I have any structures here? No. Here is an example of a molecule that is a carbonyl. I look at this spectrum, I see a strong / medium peak with, and it's messy. And the reason it's messy is because there are multiple kinds of sp3 hybridized carbon-hydrogen bonds in this molecule. But then I also see a strong narrow peak at around 1700. This is consistent with a carbonyl peak. Okay, so you're looking for a sharp peak at around 16 to 1800, and that's a good indication that there's a carbonyl. Notice what I don't know about this molecule. I know there are CH bonds, and I know there's a carbonyl. Other than that, I don't know the molecular weight, I don't know the connectivity, that's all I got. That's okay, nobody's gonna ask you to interpret the whole spectrum. Nobody's gonna ask you to solve the structure of an organic molecule based on this spectrum alone, but it does give you some information that helps you narrow the possibilities. Okay. What about this? Here you see the familiar sp3 hybridized carbon-hydrogen bond stretching, sort of a messy multiple peak centered on or around 2900. Then you see a very narrow, sharp peak, and it's not where you expect for a carbonyl. For a carbonyl, you expect the range of 16 to 1800 wave number. This shows up at around 2200 wave number. This is consistent with triple bonds. So either the only triple bonds we have in organic molecules are carbon-carbon or carbon-nitrogen. There are no other triple bonds in organic molecules. So I don't know at this point what the structure of the molecule is. I know there are CH bonds, and I know there is either a carbon-carbon triple bond or a carbon-nitrogen triple bond. If I wanted to know more than that, I could go back up to my list and see, okay, if it were an alkyne, I would expect to see an sp hybridized carbon-hydrogen bond stretch at around 3300, and it would be sharp and narrow. And as I look at this molecule, there is no strong peak at 3300. So I could say that if it's an alkyne, it's probably not an alkyne like this, because I don't see a CH bond. See the idea here? We're just eliminating possibilities. Okay, how about this one? Well, You see a carbon-hydrogen CH stretch. Again, messy and multiple peaks, but fairly intense and showing up at around 2900. Other than that, there's not a lot, though if you look carefully, and most of the time I wouldn't even bother interpreting more than that, but if you look carefully, there's some clues. There is a medium narrow peak at around 1500. This is consistent with not a carbon-oxygen bond, but carbon-carbon double bond. These ones are difficult to recognize because they're so close to this messy region below 1500 where who knows what's going on. But a sharp peak above 1500, not quite at 16 or 1700, and certainly not very deep or intense, can be consistent with a carbon-carbon double bond. And the other piece of complementary evidence that you get here, that again, mostly I might not notice, would be an sp2 hybridized carbon-hydrogen bond you expect to show up at slightly higher wave number than your typical sp3s. And you expect the peak to be medium and narrow. And so, whoops, there we go. There it is. A smaller, medium, but very narrow peak at about 3100 wave number, higher frequency than the sp3 stretch. That's consistent with a vinyl proton. So what do I know so far? Well, it probably has that structure in it. That's all I know. I could rule some things out. I know that there's no OHs, there's no carbon-oxygen double bonds, there's no carbon-carbon double bonds or carbon-nitrogen double bonds. There's no NHs. So I've eliminated a lot of possibilities, but I still don't know what the structure of the molecule is. Mostly this is giving me presence or absence of functional groups. Okay, so again, the best way to do this is examples, though I know you're interested in what kind of problems you might be asked to do. So I will post these notes, and these are just pictures of things that are in your text. You're going to need to go through this and get familiar with it on your own. Let me show you a few characteristic signals that you can use to recognize functional groups. I'm not going to do hexane or hexene because they're mostly boring. Let's do hexine. Okay, hexine has CH, sp3 hybridized CH bonds. You see that here. Hexine has a CC triple bond. You see this at around 2100. It's narrow and it's also pretty weak in intensity. And then you see this sp hybridized carbon-hydrogen bond showing up at much higher than the sp3s at around 3300. And notice this one's actually quite strong. So that is diagnostic for an alkyne that has a CH on the end of it, a terminal alkyne. Okay. Isopropyl benzene, this is messy enough that it would be difficult to interpret. So I wouldn't really bother. I would look at this and I would say, well, it's got some CH bonds in it, and it looks like it might have some carbon double bonds in it, but other than that, I got nothing. Okay, butanol, CH bonds here and an OH group there. OH, you can't miss it. You have to be trying hard not to see the presence of an OH group because it has this large, strong, deep, and broad peak corresponding to OH stretching. So look for that. It's easy to see, and it narrows the possibilities quite a bit. In contrast, this molecule that's diethyl ether, a lot of CH bonds, a lot of carbon-carbon sigma bonds, nothing there to really interpret other than, yep, CH bonds, and then some stuff I don't know how to interpret. You would not look at this and come up with this structure, but you would know, okay, it doesn't have an OH group. And if you already knew the formula for this molecule, that would limit the number of possibilities of things that you could draw. So you're going to be learning from the IR spectrum not only what is there, but also what is not there. to help you figure things out. Couple more. We won't worry about the aldehyde. Here is a ketone. Notice, yep, got carbon-hydrogen bonds, but notice the key feature, the strong, deep, narrow carbon-oxygen double bond at around 16 to 1700. Here is a carboxylic acid. Carboxylic acids generally have the OH stretch overlaps with the CH stretch, in contrast to if it were just an alcohol where they are separate. So for a carboxylic acid, you see this broad OH peak that totally coincides with the CH peak, and it's a mess. But the reason you're going to interpret that as a carboxylic acid is not just that the OH is overlapping with the CH, but also the presence of the carbonyl. If you see a carbonyl and an OH in the same structure, you're not necessarily going to know whether it's a carboxylic acid or whether it's a molecule that has a carbonyl and has an OH group. Fortunately, there are other tools we have to establish that connectivity. So for this spectrum, it's enough to say I see a carbonyl and I see an OH group. Here is a molecule that has 2 oxygens. It has 1 carbonyl. This spectrum is not enough to tell me that this molecule is an ester, but it is enough to tell me that this molecule is not a carboxylic acid and that it does have a carbonyl in it. Okay, so there's more to do. There's some stuff with NH bonds here that we could talk about, but I think we're going to skip over in lieu of how you might use this. So, as an example, you can use IR to monitor a reaction. This is an oxidation reaction of a really strange natural product. It's a bis epoxide. It's got a secondary alcohol, which if you use a chromium reagent can oxidize the alcohol to a ketone. That should result in a change, right? An OH stretch should be present in this one. A carbonyl stretch should be present in this one. So you can actually monitor the progress of a reaction spectroscopically. One of the things we haven't dealt with at all in this class is how do I know if the reaction's done? If you jump into an organic lab and start doing chemistry, the first thing you're going to ask when you set up your first reaction is, how long do I let it go? And your mentor is going to say, I don't know, you check and see if it's done. Thanks for that. How do I check and see if it's done? There's a lot of techniques. This is one of them. Okay? You would know the reaction's done if you no longer see the broad OH peak and you do see the carbonyl peak. Does that make sense? Functional group transformations as evidence of a reaction. Okay, so here's something fun. Here's a problem you might be asked to solve. Using IR and mass spec, what are some structures that are consistent with this molecule? Now, for the most part, you would be given a molecular formula. When I wrote these notes, I was using some stuff from the spectroscopy section A, where they had you calculate molecular formulas that are consistent with a certain molecular weight. I've decided not to have you do that, but it's part of this example, so we'll walk through it really quickly. So you know compound, you know you have a molecule X. What is it? I don't know. It only has carbon, hydrogen, and oxygen in it. And the molecular ion, M over Z, is 88. Okay? So just looking at the mass spectrum, there is a way to figure out, and it's sort of just empirical trial and error, what types of molecular formulas have a mass of 88. And this process is not that useful, so I won't ask you to go through it. But at the end, I had 3 possibilities that are consistent with a molecular weight of 88. C5H12O, C4H8O2, C3H4O3. All of those add up to 88. Now, you don't have to, how did I come up with that? You don't have to worry about that. I'm not going to ask you to. But given those possibilities, is one of those possibilities more likely given than another based on what I'm seeing? Well, one thing that will help if you've got a molecular formula is calculate the double bond equivalence. That'll at least tell you if you have any pi bonds or rings. C5H12O wouldn't have any pi bonds or rings. C4H802 would have one. If you do the math, you can calculate double bond equivalence. That's last time. If you can't do it, go back to the previous lecture. C3H4O3 would have two double bond equivalents. So as I look at this molecule, the IR spectrum, I see a CH-sp3 hybridized stretch, and I see a carbonyl. Carbonyl must have a pi bond. Therefore, I immediately rule out that one and all of those isomers. And among the possibilities, something that has a formula C4H8O2, I could come up with some options, and I've drawn some of them here. All of these have that formula. All of them are possibilities. But do you see how the IR spectrum is inconsistent with these two possibilities? What's missing? The big OH scoop, right? So we know it's not this. We know it's either, it could be an ester, it could be a ketone and an ether in a different part of the molecule, but whatever it is, there's no OH group. Importantly, I've accounted for the double bond equivalent. I know it's not a ring, it can't be, it has to be a carbonyl. Now, what about C3H4O3? Well, it would need to have a carbonyl group and a ring and no OHs, and these are the only things I could think of. So out of many possibilities, we're narrowing in. So far, we don't have enough to discern which of these it is, but we are at least eliminating possibilities. On your problem set for this week, I ask you to think about this for these three, it's the key, so there it is, you've seen the answers, and that was smooth. These three opioids, morphine, heroin, oxycodone. I have more to say about oxycodone later. But you can see they differ in functional groups. You should be able to use IR to predict, to distinguish between these three options. Just based on the IR spectrum alone, you would know whether your opioid was morphine, heroin, or oxycodone. Okay, I will see you next time. Have a good Wednesday.